Thanks everyone for joining. And today I'm very happy to have here Marco Cerezo, who is our good friend and also a very, I should say, a person who is leading the work in our study about Barren plateaus and all. And today he will talk about trainability, basically mostly, and prospects and challenges for training quantum neural network. So I mean, he's a postdoc at Los Alamos National Laboratory, and he has published many interesting works recently, including a very nice review paper on variational quantum algorithms. So if you really want to see where the field is going and all, I recommend that you check his review paper. And thanks, Marco, for joining, and really excited to have you here. And please start. Yeah.
Thank you very much, Kishore. Thank you everyone for attending. I'm very happy to be sharing some of the recent results that we've gotten with all of you. So I'm going to be mainly focusing on these two papers right here, but I'm going to try to throw some results from other papers that we've gotten that sort of like tie in into this sort of comprehensive work that we're trying to do of training quantum neural networks and this phenomena that we call Barren plateaus. If at any point you have questions, just please feel free to unmute your mic and interrupt me. I love questions. I love to engage in discussions. So just please go ahead and just interrupt me. So of course, the first thing that I want to do is first give a big shout out to my collaborators, because of course, some of the work that we've been doing, it has not been an individual work, but it's a big, broad band of people that we've been working with. Some of them are line scientists like Patrick, Lukash, and Andrew. Others are postdocs here at the lab, like Tyler or Akira, that actually recently joined a company in Boston called Aliro Technologies. And some of the students that have been part of our quantum summer schools and that are still working with us, including Kunal, Samsung, and Arthur. So first of all, let me try to give a very big and a very broad introduction to quantum neural networks, while at the same time trying to be very fast, because I know that it's a very broad subject and probably you will know probably even more than me in this subject. So the main idea is that we know that classical neural networks, they have revolutionized almost all areas of science. I really can't think of any area of science currently that doesn't use classical neural networks to solve some sort of problem. And of course, now with the advent of near-term quantum devices with, around 50, 60, 70, hopefully very soon 100 qubits, there is a lot of interest in trying to develop the so-called quantum neural networks. And of course, the hope is that we can harness the power of quantum computers to outperform classical algorithms on machine learning tests. And for me, it's a little bit more interesting whenever we try to do quantum machine learning on quantum data that is inherently quantum in nature. So of course, the first question is, what is a quantum neural network? This buzzword that has been thrown around for quite a while now. And the simple definition, and of course, we can't go more than this, is just a generalization of the computational model that are classical neural networks, and which is based on the principle of quantum mechanics. And in practice, just like classical neural networks, there is not a single realization of QNNs that we can point to and say, this is a QNN. There are many of them. But in general, they mostly share the same structures. So in general, what we're going to have is some problem, optimization problem that we want to solve. And we're going to encode it in a cost function. For people in the classical literature, this would be the loss function. And you're going to have some trainable parameters that you are going to encode in quantum neural networks. Those can be gates, trainable gates in a quantum circuit. Those can be perceptron weights in a quantum neural network. And you want to try to train those parameters to try to solve your optimization problem. For this, you're usually going to have some training set of data. And the goal of quantum neural networks is to employ those relatively small, noisy quantum computers to compute something that is classically hard to simulate. So you're going to take your classical data. In this case, they could be in form of quantum states. Maybe there are states of quantum matter that you want to classify by phase. Maybe you're taking classical data and encoding it into a quantum state, but you're going to send this quantum state to your quantum computer and try to perform some evaluation that you cannot do classically. And in this case, we're going to get some function that is going to depend on the parameters of our quantum neural network and on our state. And we're going to take this information from our quantum computer and create this cost function and send it through a classical optimizer that hopefully is going to be able to optimize the parameters to obtain a better solution. So we're going to repeat this hybrid loop with classical and quantum computers. And the goal, of course, if you think about now in this abstraction of the cost function, is to try to find the global minima of your cost function. If you define your cost function properly, such that in the global minima corresponds to the solution, then the goal is to just navigate the cost function and reach that global minima. And as simple as this sounds, we all know that this is a terribly, actually NP hard problem to solve, right? So there's a lot of work that goes into this very simple picture. And the output of your quantum neural network, it is of course going to depend on the task that you have at hand, but it can be a quantum state, it can be a probability distribution, a bit string, et cetera, et cetera. And of course, as I said, there are many architectures that you can use for quantum neural networks. One of the most famous and probably most used ones are just parametrized variational algorithms, where you're trying to train a quantum circuit. But you also have more general, like perception-based quantum convolutional neural networks that I'm going to talk a little bit about. And as Kishore was saying, there's been a lot of reviews lately on variational algorithms. And I will also point to Kishore's review on variational algorithms, which is also very nice, and probably you all also know about it, and definitely go and check it out. So here for me, maybe the most important question that I've been trying to answer with my work in the past maybe year and a half has been, why do we want to analyze the trainability of a quantum neural network? And by trainability here, I just very specifically will define it as the ability to take a set of parameters, run it through a classical optimizer, and obtain a new set of parameters that leads to a better cost function value. So that's what I mean here by trainability. So because those who study history are not doomed to repeat it, and we know that classical neural networks, despite their tremendous success today, they saw great periods of stagnation. They first started as single perceptron neural networks, then they were realized that if you go to multi-layer perceptrons, those are going to be better, but they were harder to train, so the backprop method had to be developed. And there's been a whole history of just back and forth between whether classical neural networks were going to be useful or not. And those so-called winters, they were very important to try to foresee them and try to come up with solutions to those problems. So of course the question is, are we heading towards a winter for quantum neural network? And if so, what are the signs, the telltale signs that we can take from classical neural networks and start to see them on quantum neural networks? And if we're heading towards that winter, how can we avoid it, right? What are the strategies that we can have to try to prevent this? And as we were discussing previously, try to still get all of that buzz that quantum computing has been building up to. So this is why I personally think that it becomes very important to analyze the trainability of quantum neural networks to hopefully try to prevent or at least foresee those winters and guarantee that quantum neural networks might actually outperform classical counterparts. So how do we actually analyze the trainability of a quantum neural network? As I was previously saying, here the goal is to take some cost function and train the parameters in the quantum neural network. And this translates into this concept of the cost function, which is you take your hyperparameter space, they can be continuous parameters, they can be such as gate rotations, they can be discrete parameters such as gate placements in a circuit, and you want to try to optimize over all of them. And we want to try to get to the bottom, to the maxima or minima of this cost function that we're defining. So here is where this concept of Barren plateau kicks in. And before going into Barren plateaus, I want to talk about precision in quantum computing, because this is going to be key, and this is why it's so important to analyze the concept of Barren plateaus. And it's essentially because quantum computers are probabilistic in nature, and this is going to be fundamental. So for instance, if I give you a very simple task, which is take a 1-qubit state that is, it could be a mixed state, it doesn't even have to be pure. And I ask, how do we estimate its probability of being on the 0 state? So it's somewhere in the Bloch sphere. So what's the probability of it actually being in the 0 state whenever you measure it? So if you ask someone that does theory like me, the solution is very simple. You just take your state, you project it onto the old 0 state, and that's your probability of finding your qubit on 0. Now, of course, reality is a little bit more complex, and we're actually trying to use actual quantum computers. So in practice, what you would do is you would just take your quantum computer, prepare your state a bunch of times, and just measure it, say, big N times. And out of all of those big N times, you're going to take those times that you actually measured it on 0, and you're going to estimate the probability of finding your state on 0 as the frequency of it actually appearing on 0 whenever you measure it. Now, this has a problem, and it is that we have some statistical precision because we're trying to estimate this quantity by sampling from the probability distribution. And this, of course, means that we're going to have an imprecision or a statistical noise, what we call this, the shot noise, by how many shots we're doing, of the order of 1 over square root of n each time that we want to estimate a quantity by just sampling from a probability distribution. So given this, this notion of measurements, let me give a non-mathematical definition of Barren plateaus, which is saying that in average, the cost function partial derivatives become exponentially vanishing with the system size. This should be exponentially vanishing as the cost function landscape becomes flat with the system size. So what does this mean? This means that whenever we want to try to estimate the partial derivative, they're going to be very small numbers, right? And not only that, we also know that we can use tricks such as the parameter shift rule, where that tells you that whenever you want to try to compute the partial derivative of your cost function, under certain conditions that are pretty general, you might be able to do this using the parameter shift rule, which is just telling you that your partial derivative is related to the cost function value evaluated at 2 points. So let's say that you're doing this trick of computing your partial derivative using this very simple formula. And now let's say that, you know, your partial derivative is going to be exponentially vanishing the system size. So that means that this quantity that you're trying to estimate on your quantum computer is of the order 1 over 2 to the n. This means that it's exponentially vanishing with the system size. So now you have 4 qubits and you want to try to estimate this. Well, your partial derivative is going to be of the order 0.06, and you might just need 256 shots to your quantum computer. This is fairly reasonable, right? In general, whenever you're either simulating your quantum computer or just actually using a quantum computer, this is not a terribly large number of shots. So you might not, this might not be an issue whenever you're trying to train a small scale quantum neural network. But of course, whenever you go to 20 qubits, now your partial derivative, oh, another mistake on this slide. This should be to the -7. Now your partial derivative's 9 times 10 to the -7. And how many shots we need to be able to estimate it so that the quantity that we're getting at is so that the statistical noise is smaller than the quantity that we are measuring, is about 1.1 times 10 to the 12 or 1 trillion shots. So you can see that this will become an issue whenever you have big scale implementations, right? Because again, because of the precision that we need when we estimate the gradient. And of course, we know that we need the gradient, or at least we need to estimate the cost function to be able to train and optimize. So this is why this becomes very relevant, because if you have an algorithm that is going to have an exponential scaling in the number of shots that you need, then it's not going to be better than your classical algorithms, because again, complexity wise, now your algorithm has an exponential scaling and it cannot be any better than your classical neural network. So any hope of advantages that you have are completely gone whenever you have Barren plateau. So that's why analyzing if your system has a Barren plateau is very important. So what can we say about Barren plateaus and trainability? And now let's just try to look at this in a more visual way. Let's say that you have a quantum neural network landscape that looks like this New Mexico landscape. And what you're trying to do is you're trying to get to the maximum of your cost function. We've defined a cost function such that the solution is at the highest point. So you might just randomly initialize your parameters. You're going to estimate your gradient using a fairly reasonable number of shots, which is not 1 trillion shots. And we're going to be able to find cost optimizing direction to hopefully get to the global minima. You might get stuck in a local minima. Sure, that's another problem that we can discuss another day, but you're going to be able to at least go in the right direction. Whenever you have a Barren plateau, what's going to happen is that you're going to randomly initialize, and you're not going to have enough shots to be able to see where that slope is taking you. So essentially what you're going to measure is just a statistical fluctuation from that 1 over square root of the number of shots that you're doing. And that's just essentially statistical noise. So whenever you're trying to optimize, you're essentially going to do a random walk, and you're not going to be able to optimize your cost function. So Barren plateaus, in a nutshell, are this problem of combining precision issues with not being able to find a cost minimizing direction. And of course, again, this becomes very relevant because what we've seen in the literature is that many people propose algorithms and then we'll benchmark them for 4 or 6 qubits. And they will say, oh, I was able to train it, so this should work for large scale implementations. And of course, here the problem is that whenever you train your small scale quantum computer, your small scale quantum algorithm, you might have a Barren plateau that you're not seeing just because you're not pushing your algorithm to large number of qubits. So this is just a cautionary tale to take into account. So of course, the first work of Barren plateaus is the seminal work by Jared McLean on the Google group, which is called Barren plateaus in quantum neural network training landscapes. And what they're doing is that they're analyzing random parametrized quantum circuits. So they just take a circuit, which they assume that at each layer, I'm just going to take some gates, I'm going to randomly place them, and I'm going to be randomly coupling every 2 qubits by doing some entanglement gate. And they analyze what happens with the trainability of this sort of architecture. So essentially what they do is that they will take one parameter, let's say the gate rotation in one of those gates, and they're going to be computing the partial derivative with respect to that parameter. And here, more specifically, they analyze the variance of the cost function partial derivative, which is just defined by this quantity right here. And in general, what's going to happen is that the second term, the expectation value of your partial derivative, is going to be 0, which is telling you that your cost function landscape is not biased in any direction. Sometimes it's going to be positive to minimize, sometimes it's going to be negative, but in general, it's just going to be averaging to 0, the second term right here. So they just look at the first term, and what they see is that for deep circuits, that means that whenever you have a polynomial number of layers where you're randomly coupling qubits, the variance of the cost function partial derivatives is again exponentially vanishing with the number of qubits. And why is this important again from this precision issue? Because we know from Chebyshev inequality that the probability that your cost function partial derivative deviates from its average of 0 by a certain value c is upper bounded by the variance divided by c squared. So essentially what this is telling you is that your average is 0, and you're going to be oscillating around 0 by something that is bounded by the variance. So if your variance is exponentially small, that oscillation around 0 is going to be exponentially small. So essentially, you're going to need an exponentially large precision to be able to find that cost minimizing direction. And this is what we call the Barren plateau phenomenon. This problem whenever your cost function becomes very flat. They were able to run some numerical simulations by taking, again, one parameter and looking at the variance of the cost function partial derivative. As you increase the number of qubits, and in this log scale, you can see that it's a very beautiful straight line, which is telling you that as you increase your number of qubits, this is going to be a very big problem. And this phenomena spans from the fact that your circuit becomes a 2 design. And this concept of 2 design is going to appear fairly regularly. Now, I'm going to ask a question to the audience here. I have this slide, an intermission about T designs, because I mentioned this concept of 2 design. Do you want me to quickly go over it? Just try to explain what 2 design is. What would you say?
Yes, please.
Yeah.
Okay, fantastic.
Yeah.
So I was talking about 2 designs and the fact that the circuit becomes a 2 design. That's actually not true. The circuit is sampling as if it were a 2 design, but I'm going to get to that in a second. So to understand the concept of T designs, we have to know what the Haar measure is. So consider that you have all the unitaries that you have of degree D, that means of their unitary matrices of D times Z. And the Haar measure is a uniquely defined measure over the unitary groups. So whenever you want to have some average of some function over the unitary group, you know that the Haar measure is essentially the uniquely defined volume measure that you will have over the unitary group of the VD, and it has certain properties. For instance, whenever you are sampling over the unitary group, that means that you're just taking your unitary groups and taking with some unitary from the group, and you're sampling uniformly. So that is essentially what the Haar measure is doing. Sorry about that, Anna. It's a little bit. It's already 7 p.m. here. It's been a long day, so it took me a while to get to the conclusion. So essentially, what the Haar measure is telling you is that you are going to be uniformly sampling from the unitary group. So this is a probability distribution. And whenever you sample from the unitary group, you have a uniform probability of getting all the unitaries. And whenever you're trying to average a function over the unitary group, you will have some volume measure, and it's going to have some really nice properties. For instance, if you have any unitary matrix A, it is left and right invariant. That means that if I take my function that I'm averaging and I multiply to the left and to the right by any unitary, I'm going to get the same result, because essentially a unitary multiplied by a unitary is another unitary. And if I'm sampling uniformly, that will not change. So a T design, now let's forget about this Haar measure and let's think about something a little bit more concrete. Say that you have a set of unitaries that I'm just giving you. It's just a collection of unitaries that has a given size. And a t-design is defined such that this set for any polynomial of degree t in the matrix elements of B and of degree t in the matrix elements of B dagger, you will have that whenever you uniformly average this polynomial over your finite set, as we have here, just by taking this simple definition, the moments that you have and the distribution that you will get is matching as if you are uniformly sampling over the unitary group by taking the harm measure. So this is the property of a t-design. And then the next question is, how is this relating to a quantum circuit? And why did I say that deep circuits become t-designs? Because again, you can think about this concept of each time that I take a set of parameters in the circuit, I will generate a unitary that this circuit is implemented. So I'm thinking about an ideal case here. I have no noise. So all the gates that I have, I can just think about the whole circuit as just generating a unitary. So by me just randomly sampling different angles in all of those gates, I will create a collection of unitaries. And if those unitaries form a t-design, then whenever I look at properties of expectation values of polynomials, it is as if I were uniformly sampling over the harm measure for polynomials of a given degree. So whenever I say that we have a circuit that becomes a t-design, that means that for any polynomial that is of degree 2 of V and V dagger, it's as if the circuit would be just taking uniformly unitaries from the unitary group. And there are some really beautiful papers that show when quantum circuits will actually produce unitaries that will form t-designs. And one of those cases is precisely the one that the Google group analyzed. So this is how this concept of t-define comes into quantum circuits, and this is how we're relating to what they're doing.
Marco, can I ask a question?
Sure.
So really, this is a beautiful idea, and has been very nicely used recently in many different works in quantum information and all. So I mean, another related, so this is basically, if I think like a way to discretize the unitary group, right? I mean, if you're like a continuous group, and you are like kind of discretizing it by using this idea of t-design. Another, like idea of epsilon nets, like people have been using to also like discretize the group of unitaries and all. I was just wondering, are you aware of any result where instead of going through t-design, people approach the Barren plateau problem through the notion of epsilon nets?
Yes, I have a slide about that 2 slides from now.
Okay, awesome. I look forward to that. Okay.
So just this concept of epsilon t-design that Kishore was talking about is essentially, now I take this probability distribution that I'm generating from my finite set of unitaries, but instead of exactly matching this probability distribution, there's going to be some difference. And that difference, if I take the norm of the probability distributions that I'm generating by taking the harm measure or my set of unitaries, that norm is upper bounded by epsilon. So that's why we call an epsilon t-design, something that is very close. And I'm going to get to
Marco, I mean epsilon nets. So like you have like a net NET. So what I mean that you have your group and you kind of like break it into grid. And
yes.
And you call that epsilon net. So a very nice paper in QIP like appeared this year, where they were looking at connection between epsilon net and epsilon net and t designs. So these are like two different ways to discretize the group of unitary. And I was wondering, whether epsilon nets could be used, like for analyzing the Barren plateau problem.
Okay, so I misunderstood. I thought that you were talking about epsilon approximate.
No.
So yes, for epsilon nets, there is a paper by Robert Huang and Preskill that came out very recently. And they actually try to analyze this concept of, you have a parametrized quantum neural network, and what happens whenever you're looking at it from a covering net perspective. So there has been some work on that recently. Yes, so sorry about that misunderstanding there. And thank you very much for pointing it out that it's something different. So, so going back to this concept of Barren plateaus, there's just another very minor thing that I'm gonna quickly go about, which is that whenever you have Barren plateau, we have this idea that the cost function variance vanishes exponentially. And a lot of people were saying in the literature, so, you might just be having this Barren plateau issue because you are just using gradient descent. But what happens if you use other optimization methods? And some people were saying maybe if you use higher order information in your partial derivatives, you will be able to train in the Barren plateau because you might be finding information about the landscape, not just through the gradient. And well, if you think about this, the result is pretty obvious, but we were also able to show that whenever you were trying to say, like, let's use higher order information and build a Hessian, and then just find the eigenvalues of the Hessian to find a cost minimizing direction. Sure, you could do that, but just getting those matrix elements of the Hessian is also going to take you exponentially many shots. And this is also valid for higher order information. And we were also able to show that even if you use gradient-free optimization methods, which are not based on taking derivatives, but rather just comparing points, like an Elder-Mead method, where you're just gonna draw a simplex over your cost function landscape and compare your cost function at different points, they are essentially still just going through this problem of I have two cost function values in a flat landscape. Those are also going to be exponentially close. So being able to say which point in my simplex is the best that I have to go towards will also require an exponential precision. So here is this concept that I was talking about of approximate t-designs, because the next question that you will ask is, well, what happens if my circuit is not polynomially deep so that it exactly forms a t-design? What happens if it has some distribution, but it's not exactly a t-design? Will I still get Barren plateaus? So here, a lot of people, whenever we were starting to look at quantum neural networks, it was this idea of, let's just try to build a quantum neural network that is as expressible as possible. That means that whenever I have my unitary group here by this gray circle, let's just try to make a quantum neural network that whenever I sample parameters from it, I'm going to get unitaries, and I want to try to cover as much as I can from the unitary group. Because then if I have problem A and problem B, maybe I can just use the same architecture to solve both problems. So here, how can we quantify this expressibility? So you can always define a super operator that is comparing what happens to whenever you have your hard distribution and the distribution that you get from your unitary. And again, you can just measure some matrix norm on this super operator. And it's going to tell you whenever your probability distribution that you're getting from the circuit matches the hard distribution, this is going to be 0. So this is a measure of inexpressibility, if you will. The larger this number is, the less you're uniformly sampling from your hard distribution. And it turns out that, I'm not going to go into the details here, but you can always show that the variance of some circuit that you have is upper bounded by the expressibility of your circuit. So that means that the more expressible circuits you have, the smaller the variance is going to be. So now you don't really have to go to a design, but you can actually quantify how bad your gradient is going to be, at least with an upper bound, for highly expressible ansatz. So maybe what you want to try to do is just use ansatz that are not as expressible as something that will uniformly sample from the hard distribution. So then the next question that you can ask is, okay, so what happens if we go, for instance, to shallow circuits? Can we still have Barren plateaus with things that do not have a lot of depth, they do not have a lot of parameters, and most likely will not have high expressibility, and they will definitely not be t-designs? So here, unfortunately, the solution is that you can still get Barren plateaus, and actually this is going to depend on the locality of your cost function. So take a very simple problem. Let me just give you this problem. Take n qubits, initialize them on 0, and just do one single rotation around the y-axis on all of those qubits, and you want to recover the 0 state at the end. So essentially, the goal is to learn the identity. And this is a completely trivial problem. We know that the solution is given by just doing a rotation of 0 angle around all the qubits, and then I start at 0 and I get to 0. But then I'm like, yeah, I know that you know the solution, but I want you to solve this on an optimizer. I want you to plug this into an optimizer. And again, we have to define a cost function. Very naturally, we could just define a cost function where I take my input state, the old 0, I just apply the circuit, and I will look at the expectation value of an operator that is just measuring the probability of all my qubits being on 0. So that if this is the identity, I start on 0, I get 0, and the cost function will exactly vanish. So this is a cost function that is going between 0 and 1, and it's 1 whenever the state that I'm preparing is completely orthogonal to the old 0 state, and it's going to be 0 whenever I'm actually preparing the old 0 state. Now, the problem with this is that if you just were to plot the cost function landscape, where I'm setting half of the angles to be theta1, half of the angles to be theta2, as you increase the number of qubits, you can see that the cost function starts to exhibit this Barren plateau phenomena. And here, this is not a highly expressible circuit. This is not a two design. This is just, there's not even entanglement in the circuit. So what's going on here? Why do we have a Barren plateau here? And it's essentially because Hilbert space is a very large space. And I'm trying to compute the overlap between two vectors that live in a very large space. I have the old zero states and the state that I'm preparing, and their overlap is going to be in average very, very small. So I'm trying to extract information from a signal that is very weak, and it becomes weaker as I increase the system size. So of course, you can always define a local version of this cost function, where instead of measuring all your qubits on zero, I'm going to measure individually one of the qubits at the same time. And in this case, by just saying, if all my individual qubits are on zero, I know that all the qubits are on zero. So these two cost functions are faithful. They will vanish under the same conditions. And we found that the local cost function does not have Barren plateau. So here, the locality of how you define your cost function for your quantum neural network might play a role in you having a Barren plateau or not. So now at this point, we sort of have two different sources of Barren plateau. The first one that is induced by expressibility, or there have been several recent results linking these also to the entanglement that you're generating in your circuit. And we also have Barren plateaus induced by globality. So of course, Barren plateaus has become this buzzword that people have been throwing around. And the question that maybe we want to try to answer when we're developing quantum neural networks is, how do we know if our quantum neural network is going to actually have Barren plateau? So maybe trivially, you would say, let's just plot the landscape and see if it's flat. But, I'm not even sure how to start. Whenever someone asks me to plot a landscape, it's a hyperparameter space. How am I even going to do this, right? I cannot visualize more than 3 dimensions. Maybe we can just randomly sample the parameters like the Google group did and just analyze the scaling of the variance. But this, of course, is very computational and demanding, because as you increase the number of qubits, you're going to have to simulate more and more problem sizes. And this is going to be very hard to do. Then you can also try to perform an analysis of try to see if your quantum neural network will have a Barren plateau. In this case, you're going to try to analytically study the variance as a function of the number of qubits. And the best one would be, if you have some information that you can use, you can create what we call some problem-inspired answers, which we don't really hope that they don't have Barren plateaus, because you're encoding so much information into your answers that you're not attempting to cover all the unitary. You just want to guarantee that the solution to the problem that you're trying to solve is included within some set of parameters. And this is actually the best that you might want to do if you can do it. And Kishore has some really nice results on this. I think that he has been pushing for some really interesting ideas for this. And hopefully, if your problem can be encoded into, if you can encode information about your problem into the answers, go for it. But if you're trying to look at general architectures, then you might want to try to do this rigorous analysis. And this is sort of where I'm going to be focusing at. So the first thing that we're looking at is what happens whenever you have this layered hardware efficient assets. So in this case, what you have is a circuit, and each layer you're going to do a 2-qubit gate acting on neighboring qubits. The main idea here is that you're trying to simulate the connectivity of a quantum computer, where it's easy to connect neighboring qubits, but connecting qubits that are not physically connected could be a little bit demanding. So we're just going to assume that you have this local connectivity, and each layer we're going to be alternating between the pairs of qubits that we're going to be entangling. So this is a sort of architecture that was very widely used in the literature. We already know that whenever you go to poly and depth, this has a Barren plateau, because this is the Google result. This is precisely what they did. So what happens is that we show that if you have global cost functions, wherever you're measuring the expectation value of some operator acting on all the qubits, this is always going to have a Barren plateau. Doesn't matter what the depth of your circuit is. We already saw that it sort of happens with depth 1. Well, doesn't really matter what you want to do. Global cost functions will have a Barren plateau. But if you look at local cost functions, whenever you're just measuring a small number of qubits, in this case, we obtain results for measuring 1 or 2 neighboring qubits for this 2-qubit architecture, then you might show that your architecture is actually trainable. And you might get some trainability guarantees to say, okay, so if my architecture has log n layers, then I know that I will be able to train this. I know that my variance is not going to be too small, and I will be able to train my architecture. And of course, log n layers might not be enough for your purposes, But maybe you can do some layer-wise training where you just train blocks of log n layers that you know that individually they could be trainable. And how do we provide trainability guarantees? Well, what you have to do is that you have to show that your variance is at most vanishing polynomially with the number of qubits. This should be omega, not O. Oh, I've already found like 5 or 6 typos in the presentation. Sorry about that. But essentially, a trainability guarantee is finding a lower bound for your variance, because then you know that it is at most vanishing polynomially with the number of qubits. And I need at most a polynomial number of samples to be able to determine a cost minimizing direction. So that's sort of like the goal that we're aiming for, polynomial scaling in contrast to exponential scaling, which is what we expect for classical methods. So I'm not going to go into the details here, but sort of what we showed, these are the 2 types of cost functions that we consider. And for global cost functions, we showed that the variance is upper bounded by a function that becomes exponentially vanishing. You can already see here that there's like some exponentially vanishing coefficients in these functions. And for local cost functions, we found this upper bound that is not exponentially vanishing. It's just going to be polynomially vanishing whenever the number of layers is in log n. And you can already see where this is coming from here. So as an example, just to show that maybe our results are very specific, because something that I didn't mention is that we assume that each one of those blocks is a local 2 design. So each one of those unitaries is uniformly sampling unitaries for 2 qubits, which is not too hard. You can actually do this with a relatively short depth circuit. I think I see a hand raised.
Yeah. Sai, can you unmute yourself and ask, please? Yeah.
Hi, yeah, thanks. So I just wanted to ask this question, Marco, whether it is coming from the row, because row, if you write a density matrix for n qubits, you have to write it as, let's say, 1 plus r dot sigma divided by something, right? And that divided by is 2 to the n typically for trace preservation. And so is the 1 over 2 to the n, is it coming from that? Is that and I can also kind of imagine that if you're now partial tracing over kind of n minus k qubits and only measuring a small number of them, 1 or 2 qubits, that partial trace will take away the 2, it will produce a 2 to the n plus 1, n minus 1 upstairs. And so you might end up with only a smaller, sorry, I'm asking a kind of, a silly sounding technical question, but I just want to know whether it's a normalization of the density matrix that's really producing the 1 over 2 to the n, or is it basically something inherent to T designs that's producing 1 over 2 to the n?
So no, that is actually a great question. So it is not exactly the normalization of your quantum state. It is coming from, and the easiest way to see this is using the Google result. So in the Google result, we assume that all of this is going to be a 2 design. And for the variance, you have to compute the expectation value of your cost function. So if you assume that V is forming a 2 design, you can use theoretical tools to perform this integration and compute the variance analytically. And whenever you integrate about that V that you're sampling over to compute the variance, you're going to get 1 over the dimension of the space where your unitary lives. And because you have n qubits, you're going to have a term that is going to appear that is 1 over 2 to the n. And it's actually coming from integrating and computing this average right here. It's not necessarily coming from your quantum state.
I see. So it's not the normalization of the state, it's actually the normalization of the unitary operator. Because in the hard random, when you try and normalize the unitary operator, you have also one.
Exactly. Absolutely. Yeah, that is absolutely what's going on. Yes. And you can always think about this from, there's different perspectives about how to go about understanding the phenomena. For instance, whenever you have local cost functions, and this was a cool insight from those entanglement-induced Barren plateau results, it's that you know that whenever you're acting with a big entangling unitary on a quantum state, and then you're tracing out a bunch of qubits, your reduced state, depending on the dimension of your reduced state and the dimension of your original state, you might get concentration of measured results. And then what you're comparing is the dimension of all your system and the dimension of your reduced state. And it's telling you that if your unitary is generating a lot of entanglement, your reduced state is going to be very close to maximal mix. So here again, what comes into place is this idea of the dimension of your original system that you're looking at.
Yes. Actually, yes, I understand.
Perfect. Yeah. So then, because our results are very stringent, you have to have unitaries that form two designs, that this might not be realistic. Maybe you're trying to do something else. So to illustrate our work, we just analyzed the quantum autoencoder algorithm proposed by Jonathan Romero. This is a proper quantum neural network implementation. You have your training set, you have your test set and whatnot. And the goal here is that you want to take a state living on n qubits and you want to compress your state such that the information lives on na qubits while you're trashing away nb qubits. So you just want all the information in your state to be compressed into this subsystem here that you can then just send through a channel and decompress somewhere else. Without getting too much into the details of the cost function, they define a global cost function, and we counter-proposed a local cost function, again, based on this idea that if I take the reduced state on b qubits and I just decouple it so that it's actually a trivial state like the old zero, it contains no information about my input state. So this is a way of thinking about the quantum autoencoder. Compression is sort of the same as decoupling. So you can see again this cost function of I measure all zero, I just measure local zero, like the one that we discussed in the toy model. And we use hardware efficient ansatz where now each one of the blocks is just some rotations around y and some control Z operation. Now, this, of course, is not a two design, but what we're able to show is that even if the conditions that led to our theorem did not hold, you will still see that as you increase the system size, your global cost function is going to become untrainable. In this case, for 25 qubits, we were not able to train it using, I believe it was a polynomial number of shots for your system. And the local cost function was always trainable. So again, this is this cautionary tale that you might be able to train for 15 qubits, but maybe your Barren plateau is going to kick in whenever you have more qubits, right? So we start to see this again. And for this super long first part of the talk, and I think that for the second part, I'm just going to go extremely fast. The main message is don't take for granted the trainability of your quantum neural network, because you might have a Barren plateau that you're not seeing just because you're looking at a very small number of qubits. And we have this connection between Barren plateaus. And of course, we already know that you can connect it to the expressibility of your ansatz and to the entanglement that it's generating, but also to the locality of how many qubits you're measuring. And this might be a less trivial way of seeing it. And of course, we want to try to give this idea of that you can guarantee trainability if you provide lower bounds for the variance of those gradients, because then you have guarantees that they will not vanish as fast. And the idea is using those tools that we use, which are essentially just using tensor networks and the wide Garten calculus that allows you to do integrations analytically over things over the unitary group, like something that forms like a two design. And the question is, can we use those to analyze other architectures, try to provide general results of whether they're trainable or not? And we tried to do this, and we were analyzing the quantum convolutional neural network. So here, the main takeaway is that the analysis that the Google group did and the analysis from our previous work, they do not apply for this architecture. So you really have to start from scratch, looking at your quantum neural network, your specific architecture, and trying to see if you do this analysis, what are the results that you're going to get, because it's truly very architecture specific. So what we saw, and just very quickly, let me try to explain what the quantum convolutional neural network is. So, classical convolutional neural networks, they're inspired by the visual cortex, and they're usually used for pattern recognition, like image recognition or voice recognition. And the main idea is that you take your information and you compress it, trying to preserve that relevant information so that you can analyze your relevant data in just a small subset. And the quantum convolutional neural network does exactly the same. You take a quantum state, you send it through a sequence of parametrized pooling and convolutional layers. In the convolutional, I'm just going to apply some unitaries, again, in this brick-like fashion. And in the pooling layers, I'm going to measure some of the qubits and do some conditional operations so that each time that I go through a convolutional layer, I'm going to reduce the number of qubits and just try to compress it and hopefully try to preserve the information in that state. Quantum convolutional neural networks, they have been employed for phase detection. You can try to use them to take states and try to say what phase they belong to. They are also used for quantum error correction. And, they're something really nice that has been out there for a while, and we want to see if those architectures are trainable. So here I'm going to skip this, but essentially what we did was use a couple of tricks where we assumed that each one of the unitaries in the convolutional neural networks form two designs. Again, this idea of independent two designs that we use that has sort of been like the battle horse for the analysis that we do. And we can simplify a little bit the quantum convolutional neural network, where we don't have to consider the unitaries in the pooling layer, because the unitaries in the pooling layer, because the operators in the pooling layer are essentially unitaries. So because of the left and right invariance, we can just absorb them into the convolutional and just forget about those measurements that could be very annoying to deal with. So here what we did was, again, try to analyze the expectation value of operators over this convolutional neural network. And what we managed to derive was, again, a theorem where we lower bound the variance of the partial derivative by some function that under standard assumptions is at most polynomially vanishing with the number of qubits. I see a hand raise. I don't know if it's the same from last time. I think it might be.
I think it is, sorry.
I think it's
okay, perfect. No, sorry about that. So we were able to develop this method where what we do is that we take the convolutional neural network. By integrating, we just map this into a graph, and we just now have to add paths onto a graph. This was a lot of work by some of our great students that were able to sort of crack this problem, because it was non-trivial, because you're tracing a bunch of qubits and whatnot. And we were able to show that under the assumptions that each one of those unitaries form a 2 design, this is lower bounded by something that is at most polynomially vanishing on the number of qubits. Now, of course, someone might come and say, but you're making a lot of assumptions. All of those unitaries, you're saying that they're 2 design, and you're saying that they're independent. Whereas in the actual quantum convolutional neural network architecture, they are correlated, so that you do the same unitary whenever you go through a convolutional layer. And here, of course, the nice thing for us is that whenever you correlate parameters and whenever you have something that is not exactly a 2 design, you expect the variance to be larger. So this bound that we found for the variance for this very toy model quantum convolutional neural network is actually also a lower bound for the vanilla quantum convolutional neural network. So this is really nice, because this means that this is an architecture that does not exceed the Barren plateaus. It just generically does not exceed the Barren plateaus. It will always be trainable. So we know that if you have this architecture and you just plug it in as part of your bigger quantum convolutional, of your bigger QNN, as maybe you're just doing some part of the analysis, at least this one right here is going to be trainable. So of course, at this point, we still know that there's more work that needs to be done to understand the trainability of quantum convolutional neural networks, with this problem that in general, the proof that you will have to do is going to be architecture dependent. We have also analyzed another type of QNNs, which are based on perceptions, and we have conditions under which they're going to be trainable or they're going to have Barren plateaus. But of course, maybe the best approach that you can do is whenever you're designing an algorithm, maybe try to get inspired by some of those methods to try to prevent or even to try to mitigate or maybe even prevent Barren plateaus from existing, like problem-inspired answers. And I cannot emphasize this so much, because they're actually one of the best solutions that we have nowadays to fight Barren plateaus. You might try to do other things like this layer-by-layer training that I was talking about, or maybe you're trying to do some smart initialization, or you're doing some pre-training so that whenever you go to your quantum neural network, you're not just randomly sampling all of your parameters. You might try correlating parameters or whatnot, but there's definitely a lot more work that needs to be done. And I don't know if I want to say locally or unlocally for us, the proofs are going to be architecture dependent. So that means that whenever you have some ideas, you're probably going to have to do this analysis again, which might be good or might be bad, because there's a lot of work to be done. And again, there's so many things to do in the field. And I think that analyzing the trainability of your architecture should become a staple for the field, so that we know that whenever you go to larger problem sizes, you're not going to have a Barren plateau. This does not preclude other optimization problems, like you might have a lot of local minima. And we know that optimizing variational algorithms is NP hard, because it's a non-convex continuous optimization problem. And there is no way that that's not a hard problem. And we have the proof for it now, which, it was as expected. But Barren plateaus is not the end of the story. There might still be other issues that we want to address. Again, locally, it's a very young and thriving field, and there's a lot of things to do. So with that, thank you very much for your attention.
Yeah, thanks, Marco. I mean, such a beautiful talk and nice summary of this exploding field of trainability in Barren plateau and all. So, okay, I have some question, but I think first probably somebody from audience can ask, and then yeah. So please like directly unmute yourself and ask. Yeah.
Yeah, I have a question. Kishore, is that okay?
Yeah, please. So Marco he's our director, like of CQT.
Hi, Marco. How are you doing?
Hey, how's it going? It's a pleasure to meet you.
Hi. Yeah, I agree in particular with the final comments you made, but let me just add a little bit of history, because I wrote the first neural network when many of you were not born. So, so the basic idea for me is that indeed we know that there are many problems where the cost function is extremely flat and you have a very hard time to get there. So as you said, Barren plateaus are a necessity because NP problems can be codified as a minimization, and therefore necessarily you should have something like that. We know that. And in particular, I want to bring back that in the 70s and 80s, people encounter the problem of solving problems with Monte Carlo. And indeed, if the cost function is very subtle, in particular when you approach a phase transition, you see that all the metropoly algorithm fails because you get rejected systematically, which is the equivalent of the Barren plateau. Now, this didn't stop us from getting very good numbers with these technologies. So what was the solution at that point? The methods that came under the name cluster methods appear. So actually what you do is that you do not look at the change in a particular angle, okay, but you do collective changes. And this in the 80s was done for Monte Carlo. So and many other methods, the same thing happens. In neural networks, again, people found immediately that it was very difficult to train till 85, where the backpropagation was invented. And if you think carefully, it's very similar to your last transparencies. Actually, you have a bottleneck in the end, and your derivative only depends on an angle. Therefore, it's not minute, it's large. And then you propagate the change little by little. So you never deal with the small changes, but with larger changes. And when you get deep neural networks, then the problem is even bigger. And the solution was to take first neurons at a time, so all the weights of the neuron, and then layers at a time. So it's always a solution is to get collective changes rather than individual changes. So the idea that the Hessian of a local angle is very small tells you that you have to accumulate this angle. And I just wanted to say that I agree with you. In the very end, you mentioned that there are very many options. So one should not be obsessed by these Barren plateaus. For instance, we started to do an analysis of the precision of these quantum neural networks for phase transitions a few years ago. And indeed, we found the small derivatives. Our solution was to adiabatically assist the training. So we started with a completely trivial Hamiltonian where the angles were known, and little by little we were changing. And we found precisions of 10 to the minus 8 in the energy. Of course, if the cost function is much more perverse, that wouldn't work. So I think, for me, the message is that Barren plateaus are there in the naive approach, okay? But we have lots of experience in the last 30 years that there are methods to bypass that. And they are very original and very clever. Genetic algorithms work very well. And another thing, it is very important to remember that often we don't need the absolute minimum. We need a good minimum. In particular, we apply neural net quantum algorithms to supply chain problems, okay, to minimization of something for a company. I mean, they're good enough minimum, saves your day. You don't really need to go to the optimal thing. So let me just say that I like very much your talk, and but in particular, I want to emphasize that this is not stopping our show, I think.
Oh, no, absolutely. And by any means, first of all, I have to say I absolutely agree with everything that you say. Barren plateaus is just a naive approach, and it just so happens that the community is still learning, and we start to see them. But I think that community is actually starting to avoid some of the things that we know that lead to Barren plateau, like using super high expressible ansatz. I'm very much aware of your adiabatically assisted VQA approach. It's a great idea of, again, trying to start with something that you know is well featured and try to go to something more complex. And yeah, you don't always need the local minima. And that's also why I personally think that some of the approaches for near term, we shouldn't just throw them away by any means. There's actually some more promising approaches like QAOA, right? In QAOA, you don't actually need to get the minima of your problem. And it's actually also super noise resilient, because as long as within some frequency you can obtain the solution, you can classically verify it. It doesn't even have to be the most probable bit string. You just have to be able to find it. So I agree that there's a lot of things that you can do to try to mitigate the problem. And at the same time, it's also interesting because some of the tools that you've mentioned from classical neural networks, I've seen them, people are starting to implement them now in quantum neural networks. And some of them have promising, some of them have results that we don't really know how well they're going to perform, like this layer-wise optimization method that I mentioned. There's been papers by Jacob Diamante saying that, it works, but in some cases it might not work. There might be some trainability transitions. So yeah, I agree that there's a lot of things that we can learn from the classical community to try to implement here. And there's a lot of super smart approaches to go about this.
So let me add just a very minor comment, just for all of us, that at the time, you may remember that Feynman, the last paper he wrote was on variational methods. That's not very well known, and it was because he was trying to apply that to QCD. Okay, and actually his paper back and back. At that time, we were reading the journals. It was back and back with Wheaton's paper. Well, some of the famous ones. So what was discovered at the time is that for many problems, the essential key was capturing the symmetries of the problem, the essential ingredient. It didn't matter the technology, the approach that you were using. If you were in a subspace that didn't have the right symmetry, you would always be off. And there were examples there were many people in the schools of Germany trying to do that for QCD. Actually, as of today, we don't have any ansatz for QCD, which is variational. Everything we have is Monte Carlo, that you respect the symmetries because you never fix gauges or anything. Whereas in the variational method, you had to fix the gauges. And it was an absolute mess, actually, no solution. So this is, to me, an example of how we have to handle things. In an extremely difficult problem, either you understand it in depth, or you may be, losing your time with a naive ansatz. Okay, as it has been in the case of QCD. Okay.
Exactly. I agree with that. That's why I always try to emphasize, Barren plateaus are not the end of the story. It's not like I'm not trying to say like, oh, we have Barren plateaus, that's it. Actually, the other way around. I actually believe that the work that people are doing on trying to come up with smart ways of solving problems is the way to go. And it's, again, sort of like a no free lunch result, right? You cannot have one ansatz that is going to be able to solve all the problems. That is not going to happen. And trying to find that ansatz is a moot point because it's not going to work. So yeah, I absolutely agree with that.
Yeah, thanks for very nice comments and questions. Are there other questions from audience? Yeah, please ask, because we have the world expert on Barren plateaus here. So if you have been wondering about, all the strategies and all, Marco is the guy to ask from. Okay, Marco, I think people are maybe shy and all, so I will take the opportunity to ask some questions like myself. So, I was thinking about, maybe it's more very naive or but I was just wondering, recently it was shown that training variational algorithm is NP hard. Now, it was perceived also as some kind of negative result and all, but it was also kind of expected that this will be the case. So let's think about, the Hamiltonian ground state problem. That's a QMA hard problem, right? And let's say if you somehow if part of the subroutine which tries to tackle a QMA hard problem is NP hard, then that's not an issue, right? Because there is already like, I mean, what we are aiming for is like a much more difficult. So to me, it was like, I mean, to me, it was like not such a bad result, right? I mean, what do you think?
I absolutely think so. I saw the paper. I was like, it is a mathematically sound proof. It's not gonna stop me from keeping working on developing variational algorithms and quantum neural networks, because we know that optimization is a hard problem, and that hasn't stopped other fields that also have NP hard problems from trying to develop clever solutions to try to get the best solution to that problem that you can possibly get. And those statements are, they're going to be either average case or worst case scenario. And in general, again, if you use like smart strategies, those results will not apply to you, right? So again, I think that we saw the paper. I think we all had like that mini panic attack where you were like, oh no, this is very bad. Then you think about it for a couple of minutes and you're like, sure, it is as expected, but it's not like it's going to be the end of the field. By any means, I don't think so.
Yeah. Okay. Then, you know, like I was wondering about this thing, like I would say, oh, I think there is a question from Chongyan, like Chongyan, he messaged me privately. Can you like unmute and ask yourself? I mean.
Oh, good morning, everyone. My name is Chongyan, and I would like to ask Marco if how local must you actually get in your local cost function in order to avoid the Barren plateau?
So in the paper, we were able to get results for operators that respect the locality of the gates that you're acting. So if you have gates acting on 2 qubits, the proof holds for 2 local. Because those will preserve the symmetries of your problem. Whenever you do the analysis, we used a lot of like light cone analysis, and those would preserve pretty nicely the analysis. We have some numerical evidence where we weren't able to get a closed form result that if you have up to log n qubits, that's still going to be trainable. More than that, you start to have a transition regime until you measure all of the qubits, and then you have a Barren plateau. But again, take into account that those results are, again, just very specific to that architecture. Like whenever you use a hardware efficient ansatz with those conditions, then you will get that Barren plateau result. And but the unpublished results that we have is that you can measure up to log n. There are other really interesting analysis that has been done. I know a paper that tries to look at, for instance, whenever you're trying to train fermionic Hamiltonians that you either use Bravik-Kitaev or Jordan-Wigner, you're going to get different locality in the operators in your Hamiltonian. And that paper actually analyzed the trainability as a function of the locality of those operators. I believe that it is by Jacob Villamonte's group again. And what they saw is that, as we know, Bravik-Kitaev leads to more local operators or fewer body. We don't have to confuse here locality with few bodiness. Locality means they're close. Few bodiness means that you're acting on 2 qubits, but those might be separate. And they found better results using Bravik-Kitaev rather than Jordan-Wigner. And those fall outside the scope of our results. So that's something that, you know, we have some evidence that the locality result might apply to more general scenarios. But again, take that with a grain of salt because it's going to be very architecture dependent.
Thank you.
Yeah, thanks, Chi, for asking. Like, are there any more questions from audience? Okay, maybe they will ask later or something. So, you know, Marco, then I was wondering, you know, like this is the local cost function is really a nice tool, you know, like which should be there in our arsenal. Like, I mean, it like if people like, I mean, I was thinking, you know, like, or have you thought about it? Like, maybe like I have a scenario and an automated way to, you know, like find a approximate or exact version of the local cost function corresponding to the, you know, the cost function which I have been given. I mean, like have some work been done, or like have you thought about it? Like,
so yeah, in some of the papers we try to derive local cost functions for papers that had global cost functions, or we try to always come up with this local approach. Unfortunately, there are some problems where it might be harder to try to derive a local cost function. So for instance, if I tell you now, you want to try to learn a unitary that prepares a state, and your cost function is just the fidelity with a mixed state. Then because that state has entanglement, just comparing it locally, whenever you're saying, okay, let me just, instead of doing like big state fidelity, let me just compare locally the states. This is going to be harder, right? Because you're not going to have a faithfulness proof that just by comparing qubits locally, you might actually get a cost function that is faithful, because you're losing information. Another problem that we had is, for instance, in quantum metrology, we have a variational algorithm for quantum metrology. And then let's say that you want to try to optimize over what measurement I should do over my state to try to get the best estimate of an unknown parameter. We know that, for instance, if you have a pure state and you're trying to learn a magnetic parameter given by a magnetic field, your base state is the GHZ, and your best measurement is just measuring X on all the qubits. And that's a global measurement. So if now you don't know the measurement, but you want to try to variationally learn it, it's global. Whenever you do a local version, let's say naively, I go from tensor product of all X from just summation of X on all the qubits. Those are very different. They have different properties, right? So it doesn't become obvious that you will be able to always define a local version of your cost function. Just as it doesn't become obvious that for all problems you might have symmetries that you might use in your answer. So for instance, let's say that I give you a quantum state and I want you to diagonalize it, and you know nothing about your quantum state. You know no symmetries, you just know that it is a mixed state. Then there are a lot of problems where, you know, it's not easy to extract information, and you might have to go to something more clever. But yeah, there's some approaches where, you know, some of the tools that we know work in some cases might not work otherwise. And again, this is completely expected.
I see. Okay. Okay, then, you know, like I had also this. I was really impressed by, you know, your paper where you like used this Pascal tree kind of a structure, and then showed that, I mean, the precision paper where you showed that if the landscape has a barren plateau, then even if you use Hessians, it will not help. I was just wondering, you know, like whether that Pascal tree kind of a structure, like, I mean, did you manage to use it somewhere like later, or I mean, like, because it's like a nice tool, you know, like to go to higher order derivatives and all. And
so I would say I've used that tool to compute higher order derivatives. It's by no means the only way that you have to do it. It's just using the shift rule again and again and again. So
yeah.
because your angles are periodic, after a while, so you're gonna start to get the periodicity back up. There are other papers that have other ways of computing this, and again, I think that paper is just, honestly, the only reason why we wrote that paper was because one referee was really telling us, if you don't use gradient descent, you will not have Barren plateaus. And it's such an obvious result that it's not true. Higher order or gradient free, it's still going to be affected. But the referee was just no. So we put out that paper.
Another one. Okay, so, you know, like, so related to that, so basically Hessians don't help us much. Let's say the landscape has already the barren plateau. So then I came in, and then there, you know, like kind of related methods, like, you know, based on quantum natural gradients have been there in the literature, right? And the natural gradients, they kind of help, like, I mean, people have used information geometry, and they have, you know, analyzed and see that sometimes they can help, you know, like go past the barren plateaus and all. So, but I mean, as a corollary of your result, can I, like, you know, understand that because you will have exponential number of measurements to even calculate the quantum natural gradient, basically you will, or am I incorrect to say that, like
it doesn't follow straightforwardly. Quantum natural gradient, it uses a different procedure. And actually, again, you can quickly derive the results, and we just didn't write a paper about this because it's just it follows straightforwardly. That if you have an ansatz that has some randomness, you're going to be able to train the parameters that are closer to your measurements, but the ones that are farthest away from your measurements are going to be harder to train. So it's actually going to depend on what the parameter you're trying to train is, the variance of the gradient. It's not straightforward that it's the same for all of the gradients. And it's, again, because of what natural gradient is doing. It's just seeing how information propagates. So whenever it gets scrambled by your ansatz, then it's bad. whenever it's very close to your measurement, it's not too bad. So,
Mm-hmm.
so in this case, it actually depends on where your parameter is. You can still use quantum natural gradient.
Okay, so you're saying that it can help against Barren plateau, like the quantum natural gradient.
It will be able to help for you to train the parameters that are at the end of your circuit.
I see. Okay, that's a good news. Then, you know, like, I mean, the final question, you know, like, I mean, I had many doubts. So like, I saw that, you know, like, very nice paper you put there where you mentioned that, and I was watching your talk and you mentioned that, you know, like, when your landscape has, let's say, like, flatness or something, then in that case, even these gradient free approaches, because suppose you use like simplex kind of method or something, it will not help, because you try to, you know, like, look at a few points and see that, you know, in which one has the smallest value, and then you move in that direction. But if I have, you know, like, flat landscape, then I cannot kind of compare and all. I was wondering, you know, like, I haven't read the paper, but yeah, sometime maybe I will read. Like Abhinav from, you know, like, Alan Asprubuzic's group, like, he put some paper where he used like evolutionary algorithms. I mean, the results were not rigorous. I believe it was more like numerics and all, where they said that it kind of helps. It kind of, no, I was thinking that, you know, like, what is the current, you know, like, consensus? Like, I mean, for like, I mean, is your result like general? Like, I mean, all gradient free approaches will fail, or is your result like a special, like, you know, for some kind of gradient free methods you made statement? So, like, I mean, can you like explain that? I mean,
so there's two things that you brought up. The first one is that if you have a Barren plateau, let's just assume that your cost function already has a Barren plateau because your ansatz, you know, it's random enough or it's global enough or whatever leads to your Barren plateau, or maybe you have enough noise that it induces a Barren plateau, then there is no gradient free or gradient best optimization that we know of that might help. Gradient free, we analyze Nelder needs. We also analyze global optimizers that are not local, because maybe we're wondering, maybe globality might help here. And it doesn't seem to work. If you have a Barren plateau, global optimizers and local optimizers will have the same problem. Then the other thing that you mentioned from Alan's group is whenever you have evolutionary algorithms that sort of change your ansatz on the fly, essentially what they're trying to do is change the landscape, because just changing the parameters is not changing your landscape. You're just looking at different regions of your landscape. But if you remove or add gates, that is actually changing your landscape. So that is another approach that people are looking at to avoid Barren plateaus. There are already many proposals out there. Stay tuned, because we're going to keep putting yet another one real soon, because it's an in-house method that we've been using. Where it's just like, let's just write a paper about what we're doing. But that is another method that people are thinking about for avoiding Barren plateaus, which is build an ansatz that maybe, again, you don't have some symmetry that you can exploit. Then maybe use machine learning to build an ansatz that works for this instance of this problem. And maybe you're going to be able to explore a region of your hyperspace that contains the solution and will not be expressible enough to have a Barren plateau. So that's another strategy to mitigate the effect of Barren plateaus.
I see. Oh, wonderful. So yeah, I mean, we look forward to your paper, like, I mean, like, on this upcoming work.